our final video in the series, we're going to look at how to balance this redox reaction using a basic electrolyte rather than an acidic electrolyte. So the first step remains the same in that we need to write our two half reactions that we're going to balance individually. And the way that we do this is simply by writing out all of the reactants and products that contain the same element in each reaction. So in our first half reaction, these are the manganese containing compounds. And in our second half reaction, these are the carbon containing compounds. If we balance our major atoms next, we see in our first reaction, manganese is already balanced, and we can balance carbon by adding a coefficient of 2 to carbon dioxide, which has the side benefit of also balancing oxygen. See that we have 4 oxygens on either side, so the only thing that we need to do to balance our second half reaction is to add 2 electrons to balance the charge. So, all that remains is to balance our first half reaction, which we can do by first balancing oxygen by adding 2 water molecules to the product so that we now have 4 oxygen atoms on either side. Next, we can add 4 H plus ions to the reactants to balance out hydrogen, and then we need to add 3 electrons, not 4, but 3 electrons to balance out all of the charge on the reactant side. Note that the permanganate polyatomic ion has a -1 charge, which means to get the charge down to 0, we need to add an additional 3 electrons to balance out the positive charge from the H+. Now, if we wanted to balance just this half reaction by itself in basic solution, we could convert the H plus here into OH minus, but I'm going to save that until we combine our two half reactions, and we'll see that it will still work out. So now we're going to combine our two half reactions, and we need to find the lowest common multiple between the number of electrons in each half reaction. 2 times 3 is 6, so this is our lowest common multiple, meaning we need to take our first half reaction and multiply by 2, and our second half reaction we will multiply by 3. So let's write out the combined reaction with these multiplications here. 2 times 3 means that we're going to have 6 electrons on both sides. 2 times 4 is 8H plus 2 of the permanganate ion. And now if we go to our second half reaction, we're going to add that to 3 of the oxalate polyatomic ion. And then if we write our products, we'll have 2 of the manganese oxide compound plus 4 water molecules plus 6 carbon dioxide and 6 electrons from our second half reaction, and we'll see that the canceling is actually easy to do because other than the electrons, we don't actually have anything duplicated on either side. So the final stage to balance out this redox reaction in basic electrolyte is to convert our H plus into OH minus, which we can do by adding 8 water molecules to the reactant side, and instead of adding 8 water to the product side, we would break these 8 water molecules into 8H plus and 8 OH minus, and we can see that the 8H plus on either side of the reaction cancels each other out. We have 4 water in the products and 8 water in the reactants, so the 4 in the products are canceled out, leaving only 4 water molecules in the reactants. And after this, again, we haven't altered the charge in any way, so if we rewrite this equation more neatly, we can double check and see whether everything remains balanced. So because the only thing that we changed was the location of the H plus and OH minus, all of our major atoms, the manganese and the carbon, should still be balanced out. And because we haven't added any new charge, because water has no charge, and 8H plus and 8OH minus, the charge cancels each other out. So that means after we write in our OH minus, all of our charge we can double check fairly easily. So 8OH minus has a charge of -8, and then 3 oxalate ions have a charge of -6, 2 permanganate ions have a charge of -2. So we can see here that even though we have this extra step to convert acid to base, our charge remains balanced. Before we conclude this video, we can take a look at a strange looking example to try one more of these balancing in base solutions here. So this looks like there is a mistake in the question because we only have one reactant, until you realize that this is a special type of redox reaction, which is what we call a disproportionation. I will say that again, disproportionation reaction. Try saying that 5 times fast. Now, a disproportionation redox reaction is a reaction that appears to only have one reactant. However, as we'll see if we write the half reactions, is that this reactant undergoes a simultaneous oxidation as it does reduction, meaning that this reaction can still work as long as we have enough of the reactant to be both oxidized and reduced. So in closing to this video, let's give this reaction a try, and we'll see something interesting and a little bit frustrating as we go through with this. So in both cases, we can see that chlorine, our only major atom in both cases, is already balanced. So we can go ahead and add water molecules in order to balance out the oxygens. Next, once this is done, we can add H plus to each side that requires it in order to balance out hydrogen. So in our second reaction, it would be 4H plus, and in our first reaction, it would only be 2. Now, we have one advantage in terms of balancing out the charge, because the charge of each of the ions that started out before we added in H plus is actually already balanced. We have a -1 charge from both chlorite and chlorate, and a -1 charge in both chlorite and chloride. So the electrons that we need to add are only to cancel the H plus charge. So if we add 2 electrons to the products in the first half reaction and 4 electrons to the reactants in the second half reaction, we find that the charge is relatively easy to balance. Now again, we can convert the H plus into OH minus now, but let's save that until after we combine the 2 half reactions into an overall redox reaction. So the the lowest common multiple is very easy to find here, because we need something with common factors of 2 and 4, and that would simply be 4. So we can multiply the first half reaction by 2 and not have to change anything about the second half reaction. So if we write out all of our reactants together, it would be 2 water and 2 chlorite ions from our first half reaction, plus 4 electrons and 4 H plus from our second half reaction, plus an additional chlorite ion, followed by 2 chlorate polyatomic ions plus 4 H plus 4 electrons from our first half reaction, plus chloride and 2 water from the second half reaction. And the reason why we didn't convert the H plus into OH minus, you can actually see here, because something works out rather nicely. So we can see that our electrons are equal in number, which means that they cancel each other out, but you'll also see that we have 4H plus on either side and also 2 water on either side. So this means that everything except for our major atom compounds cancel each other out, and if we combine everything and simplify, we can have 3 chlorite polyatomic ions in the reactants going to 2 chlorate and 1 chloride ion here. Now, the frustrating part of this is if we went to the original reaction and just did this, everything would balance out perfectly, and all of the redox balancing was completely unnecessary, for which the only thing you should be feeling is probably something that looks like this. Now, again, in disproportionation reactions, this simple solution is not always going to work out, but you can see here that sometimes we get lucky, and sometimes the overall balanced equation ends up being quite simple to find. This concludes our video series in redox balancing. In the next series of videos, we're going to look at the structure of electrochemical cells, better known by most people in everyday life as batteries.